Hi everybody, welcome. So this is just going to be a quick and to the point video, as quick as I can make it. Of course, it's probably going to be a little bit longer, but I had a patron reach out to me and ask a question, and I thought it would be worthy of doing a video on. And basically his question was, how does a transistor amplify? That sounds really simple when at first, but when you think about it, it's not that simple. How does it actually amplify? What is going on inside that little tiny piece of silicon or whatever it is that makes it amplify a signal? And so what I'm going to do is I'm going to do two parts to this in this video. The first part, we're going to do a little, what we're going to do is I'm going to read some theory to you. And it's going to be boring because I really don't have the time right now to do graphics and fancy videos. So I'm going to just put up the text on the screen and I'm going to read it to you, and I'm going to kind of explain a little bit what I'm reading. So I took these notes and formatted it, so hopefully you can stop the camera and read through it yourself, and it'll help you if you want to refer back to it later to think about what we're talking about. The second part of the video, I'm actually doing a little experiment for you to actually show you the action of a transistor amplifying. And again, it's nothing fancy, but I'm just doing this to get the information to the person I'm trying to talk to. You know who you are. And hopefully some of the rest of you may be interested in what I'm saying. Now, a lot of you who are experienced and educated on transistor theory and all that, probably going to be boring. It may even be stuff that you might say, I'm not doing a good job of getting the point across, and that might be true too. So anyway, this is my best shot at it. Take a look and see what you think, and we'll see what happens. So I think it would be a lot easier to understand how a transistor works if we go back and try to understand what a semiconductor and what a diode is in the first place. So I kind of broke it down by that, and then I moved it into what a transistor is and how it works. So what are semiconductors? A semiconductor is a material whose electrical conductivity falls between that of conductors, which readily allow electricity to flow, and insulators, which block electrical flow. This intermediate conductivity enables semiconductors to precisely control electrical current, making them the foundation of modern electronics. Now, there's different kinds of semiconductors. There are, first of all, the ones that we use are naturally occurring semiconductors. Two of them are elements that are on the elemental table, and one of them is a mineral that's readily available in nature. You can kind of dig it up out of the ground. And as they are already semiconductors. In other words, they will partially conduct electricity. But there's things we have to do to them to make them more, do a better job of being a semiconductor. So the most common that we use right now today is silicon. And silicon is a crystalline structure. It has 4 valence electrons, and that makes it ideal for controlled doping and reliable performance. And what doping is, no, it's not what you guys think. Get your mind out of the gutter. Well, we'll talk about it later. You'll see. Germanium was really the first, manufactured, mass-produced semiconductor. And the reason for that, germanium actually is not as good as silicon because it changes temperature with current a lot more aggressively than silicon does. So they can go in into what's called thermal runaway. And that's one of the negative things about germanium transistors. They also have a higher leakage. They're just not as good. And actually, Bell Laboratories and so forth, even back in the 30s and 40s, they understood that silicon was a superior semiconductor to germanium, but they didn't have the process at the time to be able to refine silicon into high purity where it would work really well as a semiconductor for like a transistor or a diode. Germanium had a lower melting point and was easier to make high purity than silicon. And that's why you saw these first. And then later on, when they perfected the process for silicon, then they abandoned the germanium for the silicon, which is a better semiconductor. The very earliest ones, though, was galena crystals, which is a lead sulfide. So lead sulfide exists in nature. You can find it in the ground. You can dig it up. And it actually was what a lot of very early cultures used to make lead. They could burn it with just wood-based fires, and they could extract it, melt it down, and get the lead out of it and use it for lead, which was very common to make things out of back then because it was soft and easy to work with. But galena also has a semiconductive property, and really you don't have to do anything to it other than use it. And that's what the old cat's whiskers, crystal radios used. They used a galena crystal. If I have some pictures of this stuff, I'll put it up there as I'm talking about it. But it really, really was very inefficient compared to these, and really didn't work as well as actual silicon and germanium, which these are two actual elements on the periodic tables. Now, how do we make an actual semiconductor work better? Well, we can split these and we can make these semiconductors work more towards, positive charge or negative charge. And we do that by adding an impurity to the purified silicon or germanium. And that process is called doping. So the first thing they do is they make high purity silicon or high purity germanium, and then they dope it, or they add an impurity. So modern semiconductors achieve their remarkable versatility through doping, which is the controlled introduction of impurities into pure semiconductor materials like silicon. This process allows engineers to precisely tune electron flow characteristics. N-type semiconductors are created by doping the silicon with elements that have 5 valence electrons. So those are the pentavalents. So a pentavalent, penta meaning 5, makes an N-type semiconductor, such as phosphorus or arsenic. So they take phosphorus and arsenic, they mix it with the high purity silicon, and it makes it an N-type semiconductor. These donor atoms contribute extra electrons to the crystal structure, creating an abundance of negative charge carriers. The N designation comes from the negative charge of these excess electrons. Okay, so you're making half of what we need to make a diode. The other part is called the P semiconductor. And P-type semiconductors result from doping silicon with elements having 3 valence electrons, which is called a trivalent. And a trivalent is, 2 examples would be boron or aluminum, and they use those to create an impurity in the silicon or the germanium, whatever it is. And they'll actually have a positive charge carrier to them. So these acceptor atoms, as they call them, create what we call holes. A hole means that there's an area for the element to absorb more electrons or attract more electron charge. So there's electron deficiencies that act as positive charge carriers. So the P designation refers to these positive charge carriers. Okay? Boring, but we need to know all this stuff. So the PN junction is really what you need to have a basic diode. So when a P-type and an N-type material is joined together, they form what's called a PN junction, and which is the fundamental building block of diodes and more complex semiconductor devices. This junction creates a remarkable one-way valve for electrical current. So again, we were using that whole idea of water, with valves and switches, pipes and so forth. It makes it easier to kind of imagine how it works. So here's the big thing. When you put this PN junction together, where they join, you're going to have a region in the center called a depletion layer. And they do that by how they create that junction and fuse the 2 elements together. And if you notice, there's an arrow going both directions, okay? So first of all, at the PN junction interface, there's a critical process that occurs. You have charge migration. So electrons from the N-type region naturally diffuse towards the p-type region, while the holes from the p-type region move toward the n-type region. Depletion zone creation is when the electrons fill holes near the junction, they create a region depleted of free charge carriers, and this depleted region contains fixed positive charges, which is ionized donor atoms on the n side, and fixed negative charges, ionized acceptor atoms on the p side. This creates an electrical field that opposes further charge movement, establishing equilibrium. Now, basically what happens is in the beginning you have this depletion layer in here, and you notice the arrows are pointing both directions. Well, what happens is as we start applying a charge, if we forward bias it, in other words, we put the negative charge on the correct side, with the positive, what will happen is that depletion region will shrink. It'll go down. As it goes down, eventually the electrons will go from the negative side to the positive side, and it'll cause current to flow. Now, the opposite happens when you reverse bias the diode. In other words, when you put the negative onto the anode and the positive onto the cathode, what's going to happen is current's not going to flow because the depletion layer is going to get even more filled up with charges, and it's going to increase that depletion layer. And this is kind of like the no man's zone, where no man's land, where nothing can get from one side to the other. And again, when we put a reverse charge on the diode, it blocks it. So that's what causes a diode to conduct in one direction, but not the other, because you have this P and N junction. So they'll line up with the charge of your battery or whatever the heck voltage source you're putting on there. So what good is that? Well, if we want to control the flow of current and make it only flow in one direction, that's what this is designed for. So in one direction, current will flow, the other, it'll block it. And one caveat to that is to get over this depletion layer and to get this to go through, you're going to lose a certain amount of charge. In other words, there will be a actual drop of voltage, and that voltage drop is kind of lost. So if I have, the voltage drop is determined by the design of and the actual element of the silicon or germanium or whatever. Silicon, for instance, in a properly designed silicon diode, just a standard one, you will have a forward voltage drop or a loss of voltage of about half a volt, anywhere from 0.6, 0.7 volts. And as the temperature of this changes, it actually will change how easily this charge area will be able to react or not react. So that forward voltage drop will change with temperature. And that's what these two arrows are telling you, that if you're drawing heavy current through this, a lot of electrons are flowing all at once through here, this will heat up, and that heat will cause the depletion layer to get even smaller yet, and it'll cause current to flow even more easily, which could create more heat. In a germanium diode, that was a problem. If you exceeded the current of this and it began to heat up, it would be a self-feeding monster until finally the transistor would burn up. And you had to do things in the circuit to protect against that. Silicon handles heat a lot better, and it's a lot more stable with temperature changes than germanium is. So that voltage drop will vary maybe, a couple hundred millivolts, but that's it. It's not going to move massively like it would in a germanium diode. Now, other types of diodes like Schottky diodes and things, they're doped in a different way, and they have a smaller forward voltage drop and some other properties that make them a little more interesting. But I'm not going to get into all that. Okay, so really, just so you know, that's how a diode works. Now, just as I was saying, diodes behave under different bias conditions. Bias just means how much voltage you have on one side versus the other, what the voltage potential difference is, and in what direction the charge is. So in forward bias, when an external voltage is applied with the positive terminal connected to the p-type side and the negative to the n-type side, the applied electric field opposes the built-in field. And this reduces the depletion region width. See, I underlined that because that's what's happening here. That's back to these arrows. And which lowers the energy barrier for the charge carriers. The electrons and holes can now flow across the junction and recombine, allowing substantial current flow. All right, so I'm not going to get into recombination or anything like that because, again, I'm already getting way too much into this, but it helps you to understand what's going on. Reverse bias is when the voltage is applied in the opposite direction. So the external field reinforces the built-in field and widens the depletion region and increases the energy barrier, which effectively blocks the flow of current. So only a tiny leakage current can flow due to thermally generated minority carriers. So again, if you reverse bias it, it'll block the flow of current, but only to a certain degree. There is what's called a breakdown voltage, which I didn't put in here. And at a certain point of time, that potential becomes so high that it can start conducting in the opposite direction. But what you'll find is whatever the breakdown, that's called a breakdown voltage, whatever that breakdown voltage is, that's how much the voltage drop will be. So really what you can think about it as, in forward bias, you have a voltage drop of less than 1 volt, but in reverse bias, you have a voltage drop of many volts. You know, for instance, a 1N4007, which is your very basic garden variety diode, it has a reverse breakdown voltage of 1,000 volts. So you have to apply more than 1,000 volts to that diode in reverse before it'll start to conduct backwards. And then it will drop off that 1,000 volts, roughly. Okay, I'm just kind of being simplified here, but that's what happens. So there you go. That kind of explains a diode. All right, and I put a little schmeal in here on some of the things we use it for, and you can read that if you want. All right, so now knowing what we know now about diodes, we can better understand how a transistor works. Because a transistor is basically taking 3 elements and combining them into kind of a sandwich of 3 different parts. So for instance, this is showing an NPN. Well, let's read this first. Similar to the diode, transistors also use the PN junction. Only in this case, there are 2 junctions which form a type of sandwich. The center element, which is called the base in the sandwich, which is this part right here with the circles, is always the opposite polarity than the outer elements, called the emitter and collector. See that? So you see how this has the holes, and these ones have the negative electrons. Now, in the case of like a PNP transistor, they would have that P material with the holes as the collector and emitter, and they would have the N material, which has the electron charge, or the negative charge, as the base material. And what that means is that you would have to apply the voltage in the opposite polarity to get current to flow. And there's advantages to having that. So when you're designing an electronic circuit, that's why both types of these exist. In vacuum tubes, there's really only one polarity of vacuum tube, and it's the most similar to an NPN transistor. There is no such thing as a PNP version of a vacuum tube. So in a vacuum tube, the grid always works, by applying negative voltage to turn it off and positive voltage to turn it on. And that's just how they work. So kind of the same way as an NPN transistor. But that's kind of where the similarities end. So the junction at the base and emitter will act like a diode. So in other words, from here to here, it acts just like a diode would act. It's a PN junction. And when you apply current to the base to emitter, current will start to flow just like a diode. It'll go one direction but not the other. But it does something more than that. Notice you have two depletion regions. You have a small one between the emitter and the base, just like you do on a diode, but you have this larger one between the collector and the base. And what's going to happen is, as you cause a little bit of current to flow through here, you don't need a whole lot, this will start to shrink rapidly, and it'll start to allow current to flow. If you put a voltage source here as well, it'll allow current to flow from here through the base junction and out through the emitter. And here's the cool thing about it. Well, I'll read it because it's kind of spelled out in here. When forward biased, it will conduct just like a diode does. This in turn will also cause the junction at the collector base to conduct current through the base emitter junction, and the amount of current flowing from the collector to the emitter will be greater than the amount of current flowing from the base to the emitter. In other words, you only need a little bit of base current to allow a large amount of collector current to flow. That's really what I'm trying to say here. All right, my wording might not be that great, it's a magnitude difference. In other words, it can be anywhere, like I said, from a few times, like big high power transistors usually have low amounts of difference, to many hundreds of times. So like some of these little tiny transistors like this, they're called small signal transistors. They can have 700-800 times. Even there were a few made in, back when, really in the heyday of these, that were up to almost 1,000. And then you can get into Darlington transistors, which is basically two transistors connected together inside one package that can be tens of thousands of times of more current flow. And we call that the transistor's gain. So in other words, the ratio from how much base current you cause to flow that causes collector current to flow, that ratio is called the transistor's gain. Now, when you're just talking about, I apply a voltage here, a current here, and I get a current here, that's called the beta. And the symbol for that is the letter B, the actual Greek symbol for B. It's that weird B with the line. Anyhow, but it's not a very good measurement because there's so many things. Like I said, temperature affects all of this. Temperature will affect these junctions, and it will affect this. Also, if you're putting a changing voltage, in other words, like an AC signal, like you're putting audio in an audio amplifier or whatever, or a waveform through there, the frequency of that signal also will affect the ratio at which, how this gain works. So when you measure that under a very specific set of conditions, this much current at this much voltage at the collector and so forth, we call that HFE. And that is the H model of the, what the heck is it? I forget what it stands for, but basically it means that HFE just means the beta at a certain set of test values. That's what that means. And to determine what, how much collector current is going to flow, you take the base current times the gain, or the HFE, or the beta, whatever, and that's going to equal the amount of current that's flowing from the collector to emitter. In a nutshell, that's how it works. Now, there's all kinds of variables that affect that, but that's how it works. So how does a transistor amplify? It amplifies by the action of these junctions here, and how these depletion regions change at different rates. So by changing this a little bit, it changes this one a whole lot. And that's what the amplification comes from. Now let's do a little experiment and see just how this works. Okay, so here is our little experiment. And this is a drawing. Now what I wanted to do is I wanted the most simple amplifier circuit I could possibly make. And we're not talking about amplifying an AC signal right now. We're just talking about how we are going to use a small amount of current to control a large amount of current, because that's really what amplification is all about, using a smaller signal or smaller amount of energy to control a larger amount. So I came up with this little circuit, and it only involves one resistor. It is actually using the internal shunt resistor of my milliamp meter as the load. And those are the only two components other than the transistor. And we're going to just feed it with 5 volts. Now, one thing I will tell you, in case I know some of you get worried about damaging test equipment, I actually am using a current limited power supply so that if something were to short out, you wouldn't overload the milliamp meter. That's all. So we're safe. Okay, so if we screw up, we're okay. Now, what I'm doing is this RB, that stands for the base resistor, because this resistor is connected to the base of the transistor. This is an NPN. And I'm using a resistance decade box. And the reason I'm doing that is so we want to know, we could put a pot in there and vary the potentiometer and do the same experiment, but we want to be able to know exactly what resistance we're working with here when we're measuring all this. Now we're going to take 3 measurements, and what I've done is I've drawn a little card, little cheat sheet card for each meter where it is connected in the circuit and what it's measuring. So if you look here, this one's measuring the actual voltage drop across this resistor. All right, and you can try to guess what's going to happen when I change the value of this resistor. All right, so we're going to check the voltage drop across the resistor. This one is going to measure the voltage drop between the base and the emitter of the transistor. So I'm just going to measure the VBE, or the voltage from the base to the emitter. And last of all, we're going to measure the current flowing through the collector to the emitter. All right, so this collector emitter current, we're going to measure it. Now, why am I not measuring current here? Well, it's kind of a tricky situation. What I want to do is we're going to measure the voltage, first of all, to demonstrate something. And then we're going to use Ohm's law, because we know we have a voltage, we have that measured, and we know what resistance it is because we're using this decade box, and we can use that to calculate the current. And since this is a series circuit from here through the resistor, through the base to the emitter, the current at any point in this circuit is going to be the same. So if there's so many microamps of current flowing through the resistor, we know that the base emitter current is going to be that same amount of microamps or whatever. So we can actually measure the IBE, or current from base to emitter, by measuring the voltage drop across this resistor and doing the math. So let's turn everything on and we'll see what happens. Okay, so I have these turned on. This meter is set to measure volts. This is set to measure voltage in the range of millivolts. And this is set to measure milliamps. And I'm on the 10 milliamp scale, I believe. Yeah, see, 10 milliamps. All right. And again, just this is where we are. Now here's the little tiny transistor. It's buried in these wires on this breadboard. And here's our decade box. Now right now, I have this set to 1 mega ohms. So this resistor right here is 1 million ohms. 1 million ohms. Okay. So let's turn on the 5 volts. And you can see the voltage drop from the base to emitter is about 600 millivolts. And if you recall, everybody talks about the 700 millivolt drop on a silicon transistor. Well, this is what they're talking about. And every transistor is a little bit different, so you're going to be plus or minus, you know, a couple hundred millivolts. So this can be anywhere from, depending on the transistor, you know, several hundred millivolts up to almost 1 volt, depending on the temperature of the transistor. Temperature and things affect the transistor. So for instance, if I take a heat gun, and I'm not even going to change any voltages or anything, watch what this does when I blow this heat gun on there. See what happens? And then it's almost instant. And you see how the VBE dropped? And this one conversely went up a little bit because it's a voltage divider between here and here. All right? And if we blow a little bit of cold air on it, get some freeze spray. You can see it shoots up. Just for a little bit until it warms back up again. So temperature affects this, all right? Now, if you watch this, if I do that, notice how that goes up ever so slightly. It's hard to see, it's very little, but it affects it. All right, so now that we kind of know what's happening, I have 4.4 volts across that resistor right there. And if we do the math, I equals E over R. So if I take 4.41 divided by the resistance, which is 1 million, right? There it is. You have, this would be milliamps. You have 4.41 microamps of current flowing right now. So 4 microamps of current is going between the base to the emitter. 4 microamps. But if we measure the output of the meter here, I'm on the milliamp scale, and you can see 10 milliamps is here. This is 1, 2, 3, 4, 5 milliamps will be in the middle. We're a little bit over, we're about 1.1 milliamps. When I put my hand near the meter, the static on my hand moves it. But you have 1.1 milliamps. So 4.41 microamps of current is controlling 1.1 milliamps of current. Now, I have a question before I start this. I want you to ask this. When I reduce this resistance, I'm going to now make the resistance lower across here. What do you think is going to happen to the voltage on the resistor? Will it go up? Will it go down? What will it do? Let's do it. So I'm going to go from 100 or 1 million ohms. Let's cut it in half. Let's go down to 500K. So there's 500,000 ohms. What happened to the voltage? It didn't move. What happened? What happened to this voltage? It really didn't move. But I changed this resistance. Well, this is a voltage divider here, all right? And the voltage drop across the base to emitter junction is always going to be around that 0.6, 0.7 volts. And it's only going to change a little bit as more current flows through the transistor and the transistor heats up. It will drop a little bit. But other than that, you're still going to have a voltage divider between two things. And if one voltage is always fixed, then the other voltage dropped across the other resistor, which is here, will always be fixed. It'll always be that multiple of the 5 volts. So no matter what resistance I set this to, this is always going to be this voltage, but the current is going to change. So let's do the math. Remember, it was 4.41. It's now 4.45 because the transistor is running a little bit warmer. And you can see, instead of 1 milliamp or 1.1 milliamps, we now have 2 milliamps flowing from the collector to the emitter. So if I take the 4.44 volts divided by 500,000, I now have 8.88, just about 9 microamps of current. So I have 9 microamps controlling 2 milliamps. So that's how an amplifier amplifies. I use a very small amount of current to control a larger amount of current. Now, just so you know, that base of that transistor is very, very sensitive. And remember, people think of super sensitive when they talk about MOSFETs. You know, everybody says don't touch the gate of a MOSFET because your static from your fingers could damage it. Transistors are not, you know, they're pretty sensitive too. Case in point, if I unplug these, okay, so now I disconnected the power, you know, this resistor. I took the power away. Notice how there's some voltage there. And watch, just touching with my fingers, see there? I'm actually making current flow from the collector to emitter. You see that? And I have a half a volt drop, or 0.6 volt drop across my body right now. Just the resistance of my body is enough to make the transistor conduct ever so slightly. And notice when I let it go, the voltage doesn't just drop to 0 right away. It goes down slowly. Watch. See that? And that's because the transistor actually has a little bit of capacitance in it. So even the meter itself can affect this, because this meter has a 10 mega ohm resistance. It has an impedance of 10 meg. So anything that this meter connects across, it's putting a 10 million ohm load across it. So if I pull this lead out, notice that changes. And notice that changes. It goes up a little bit. Watch when I plug it back in. See how it changes? And when I unplug it, so even that huge amount of resistance adds enough voltage or enough current, let's say, that it drives the transistor, turns the transistor on a little more. So you can actually see the action of how this thing amplifies. Now, if I go down in resistance, these voltages almost don't change at all, but the current is changing because the overall amount of resistance between that 5 volts and this ground here through the emitter, the resistance is dropping. So because of Ohm's law, the current is going up, even though the voltage is the same. See that? So I'm now down to 200K or 200,000 ohms. And you can see now we have 6 millivolts flowing. And if I do the math now, 4.3 volts, let's say 3.5 volts, divided by, what is it, 200,000. And you can see we now have 21 microvolts, or microamps. So instead of 8 or 9 microamps, we have 21 microamps. But still, for 21 microamps of current, we're controlling 6 milliamps of current. So you see, that's what we've amplified our signal. So what is all this about bias? Why do we need that? Well, here's the thing. I can put so much resistance on here that the transistor pretty much turns off. So for instance, if I disconnect this altogether, you can see there's no voltage between the base and emitter now. So there's no current flowing through the collector to emitter. And as a result, the transistor is turned off. So if I just put a signal right now, like an AC signal, anytime the signal goes up or goes positive, the transistor will pass that signal through and it will amplify it. But as soon as the signal goes negative, the transistor is already turned off. It can't go any further, so it'll basically clip off the signal. So if I were to put, for instance, a 1 kilohertz sine wave like this into it, what I'd get out would be this. It would look like that. And this whole bottom part, this whole negative going part would be cut off. So why do we bias the amp? Well, if we turn this transistor on about halfway, then what will happen is by turning this on about halfway, when I feed a signal in there, when it goes positive, it'll turn the transistor on harder. So it'll make more current flow. But if I turn the transistor, if I put a negative going waveform, it will it'll add to this positive voltage, and a positive voltage and a negative voltage will cancel each other out somewhat. So if I put, some negative signal, it'll subtract from that voltage there, and the signal will go down. And that's the whole reason you put bias voltage on an amplifier like this. Now, when we set this to exactly half of its operating point, we call that class A. And that's basically how we get a single transistor to be an amplifier. Class A means the bias has the transistor running at about half of its total range. And then we can go up or down from there. So right there, the transistor's on the whole way. If I go down to 100K, you can see it pegs the meter. And I start drawing too much current. So what we want to do is we want to have it, we're just going to say we can go about that high now. And then I can add a signal to it. And of course, we need an oscilloscope to see it, which we'll hook up. And you can see how the transistor actually amplifies. Okay, so what I'm doing right now is I'm taking my signal generator and I'm connecting a capacitor. The capacitor will block the DC from here, so it doesn't see that, and it'll only allow the signal to pass through here without allowing the DC to feed back into my signal generator. Like that. And you can see this mess here is the probes. And right now what I'm looking at is I'm looking at the signal right here with one probe. That's with channel 2. And channel 1 is right here, and it's just looking at the output of the transistor. So let's take a look at the signals. I'm not going to turn this on for long because driving it this hard actually will make the transistor heat up. So I'll turn it on right now. And you can see how everything is working. And if you look up here, I have a very noisy signal on my transistor right now because everything's out in the open and this breadboard doesn't have very good contacts. It's getting worn out. I'm going to have to throw this breadboard away. But you can see we're on the same scale, 50 millivolts per division in each one. And the blue signal is the signal going into the transistor at the base, and this is at the collector of the transistor. And you can see how much we're amplifying that signal right now. And of course, if I turn the signal down on my signal generator, it follows it. See that? And that's how a basic amplifier works. And the transistor is a bit warm to the touch, but it's not burning my fingers. But if I would have put even more current through it, this would actually be able to go a little bit higher, but we would need a heat sink on there to carry away the excess heat, because as that transistor delivers that current, some of it is converting into heat, because again, only part of the signal is getting to the output. The rest of it is being absorbed by the transistor, and therefore the transistor will get hot. That's why you have heat sinks on transistors. And that's what biasing is. Now, if I change the bias voltage, so what I'm going to do is I'm going to adjust the resistance on that resistor box while we're running this amplifier. I'm going to make the resistance higher. So that's going to lower the bias. Let's watch what happens to that output signal. Okay, here we go. So now I'm going to add 100 kiloohms. And you notice how it shrunks very quickly. And notice the bottom part of the waveform is coming through, but the top is starting to get clipped off. And as I go higher and higher, and I turn the transistor more and more off, now instead of an amplifier, it's a de-amplifier, right? It's unamplifying. It's attenuating the signal. And that's how it works. Now, the other thing is, since we're measuring the output, let's turn this back up. Since we're measuring the output at the collector, notice one thing. These are out of phase with one another by about 90 degrees. So you can see as the input signal is going up, the output signal is going down. So it inverts the phase. Now, we could rearrange the circuit. Let me turn this off here. We could rearrange this circuit, and we could take our milliamp meter and put it down here, and we could put our 5 volts directly in here, and we could measure at the emitter, and that type of circuit is called an emitter follower. And the reason that it's called that is because the emitter will follow the signal at the base. In other words, instead of being 90 degrees out of phase, the signals will then be in phase with one another, like that. But emitter followers typically don't amplify as well as a collector, common collector circuit like this. So that's why you typically see this type of circuit. This gives you better amplification, but if we do the emitter follower, then you're going to have it'll be in phase, and it also has to do with the output impedance, the load that it can drive. And we won't get into all that in this, that's too much, but at least you kind of get an understanding of how it amplifies. And remember, it amplifies current. Even though we're putting voltages in there, we're measuring a voltage level. That voltage is just affecting the load as to how much current is flowing through there. So it is a current controlled device. Now, real quick primer with a MOSFET. Very similar circuit, except the gate, and you have a gate and you have a source and a drain, and the gate is driven by voltage. So it's a voltage controlled device. By having a higher voltage potential on the gate, it causes more current to flow through the source and drain. And so you have to understand that a MOSFET still controls current, but it's using voltage to control current instead of current to control current. That's the main difference between the two. Okay, so some of you are probably more confused than before I started the video, and some of you are saying I have that aha moment. I hope that's what most of you have. And some of you are saying, nah, I already knew that. But either way, I hope it entertained you a little bit. I know I had fun doing this. It was review for me because honestly, I haven't had to think about these things for a long time. And you can see that in a lot of my videos when I'm working on a stereo or something. There's a lot of times that I just don't remember this stuff if I don't look it up. And if I just try to pull it off the top of my head, there's so much crap in here right now that sifting through it and finding that little bit of information I need gets harder as time goes by. I can tell you that right now. So, hey, you got to laugh at yourself sometimes, huh? So again, I hope you all liked it. And now that I got things cleaned up here, I hope to be getting a few more videos out a little more often. And until then, I wish you all, as always, peace, joy, happiness, and good health in your lives. And hope everything's well with all of you. And I can't wait to see you next time. Take care, everybody. Bye-bye.